Hi, my name is Arvind Krishnamurthy, and today I would like to spend a few minutes talking about networking fabrics and what they mean for machine learning. In particular, I would like to focus my attention on significant hardware advances which are taking place in this space. Just as a caveat, I'm not a hardware expert, so I'm going to be mostly painting fairly broad strokes, but I would like to convey the excitement that I feel in this particular space and would like to encourage you to go off and learn more about these various different things and make great use of them. So, the networking hardware is really advancing at different levels of granularity within the cluster fabric. So within a server, we are starting to see both proprietary as well as open standards which are showing up. We are starting to revisit the question of what is a rack and what should be a rack scale interconnect. And and ML, of course, imposes a lot of needs from the cluster regarding both efficiency and cost. So we're seeing a great number of innovations in that space as well. So let's dig into each one of these things in greater detail. So at the server, uh, there's significant focus on new interconnects, which provide high speed as well as low latency links. We are starting to see chiplet to chiplet communication standards such as UCIe, new protocol standards such as CXL, which updates PCIe, as well as proprietary solutions such as NVLink C2C. What all of these have in common is that they provide a memory address space semantics, such that all of the disparate heterogeneous compute elements are interconnected and can access each other's memory in a fairly transparent manner. And this provides great degree of memory expansion. It also provides the traditional load store access model along with atomic operations. But it also provides cache coherence. That is, if some element gets updated and is being cached by some other element, then the cache coherence is going to ensure that you have proper synchronization between these different elements. So as an example, what we have is here is the Grace Hopper superchip. The Hopper GPU is connected to the Grace CPU at fairly high throughput. And now the Grace CPU's memory can augment the GPU's high bandwidth memory on the Grace Hopper superchip. And that, of course, means that you can do things which you couldn't have done before. Moving on to the rack scale, we are seeing some tremendous accomplishments with respect to interconnects. And one way of thinking about this is that the rack has become the new server. There is all of the uh, throughput and latency characteristics of a server are now available at a rack scale. So consider, for instance, the NVL72 architecture. You have 72 GPUs, which are spread across essentially 18 servers or CPUs. And all of these 72 GPUs can access each other with per or GPU to GPU throughput of 1.8 terabytes per second. And you can also perform load stores at 300 nanoseconds across these GPUs. So what we have is essentially immense amount of integration, providing a unified memory model, and you're also having a load store interconnect, but not necessarily cache coherence, as you might have seen with the server interconnect. And then moving on to the cluster fabric, the focus is really on developing low-cost solutions, trying to come up with specialized topologies, as well as coming up with custom functionality which are suited for machine learning. Since these are cluster scale solutions, you actually need longer reach, so optics becomes a requirement. And since optics is a requirement, you want to reduce the cost of optics. So we are seeing co-packaging of optics along with switches and along with servers, and these promises substantially lower costs and also lower energy requirements. We are also starting to see fairly custom topologies which are suited for machine learning. So So we know that GPUs of a certain rank communicate with each other, so why not connect GPUs of the same rank together using rail optimized topologies? Or in the context of TPUs, we have a three-dimensional torus mesh network which connects all of the TPUs together. We're also starting to see a lot of new proposals on custom topologies which are built using optical circuit links so that you don't have all-to-all connectivity between all of the GPUs or TPUs, but rather a fairly sparse connectivity. And the assumption is only certain accelerators will need to talk to certain other accelerators at any given point in time. And since machine learning requires things such as collectors, we are also seeing the integration of these aggregation capabilities into the switches themselves in the form of in-network aggregation. So these are all pretty amazing innovations. And the question that we are left with is how do we evaluate um, the utility of all of this emerging hardware? And I think these fabrics must be assessed against the requirements of all of the emerging ML characteristics. And what I mean by that is that we are starting to see much larger models, often structured as mixture of experts models. They have much larger memory needs. But more importantly, not all of that memory of the model is actually activated at any given point in time. So what does it mean to have sparse activations in that context? And the size of these models also translates to much larger contexts as well. So especially in agentic settings where an agent remembers everything that's happened in the past. And but much of that context isn't actually relevant to a specific inference request. So will these emerging hardware help with that kind of much longer context, which with sparse attention on those contexts? And we're also starting to see uh, inference time innovations such as thinking agents. These are generating much longer generations as part of inferences. These are increasingly memory bound, and they also use much sparser attention. So the takeaway really is that ML is getting bigger, sparser, irregular, and distributed. And we need to understand how this emerging hardware helps in the context of these ML changes which are taking place. So the question that I'm particularly interested in is really understanding whether this new types of hardware reflect new inflection points. As in, do these innovations reflect uh, a sort of a new capability where these tighter integrations enable something that wasn't actually possible before? Or is it actually the case that this integration, which is being performed at a much larger scale, we can we don't necessarily need it, and we can actually make do with what we currently have, which is the status quo, which is not necessarily such great throughputs and not necessarily such great latencies. So let me elaborate on this a bit more in the context of each one of these different types of networking hardware which is showing up. So consider, for instance, the host GPU integration. Is that a breakthrough? So clearly, inference workloads can actually benefit from integrating the host CPU's memory. And they might also be able to benefit from integrating the host CPU's computing capabilities. So for instance, you can do just-in-time offloading and onloading of weights and KV state. And here the question then becomes, is the channel between the CPU and the GPU providing sufficient bandwidth to do this just-in-time onloading and offloading without actually keeping the GPU from wasting its cycles? And so we know that this channel is now substantially higher throughput, but the question really is whether is it high enough throughput to keep the GPU busy all the time? A related question here really is that you have host CPUs which have some computing capabilities and which have access to much larger CPU site memory. Can we now integrate the host site CPU along with the GPU computation such that it can perform certain irregular sparse computations? And if you can actually do that and take advantage of the cache coherence between the host site CPU and the GPU, then we might actually be able to enable efficiency gains and integrate the CPU computing capabilities in a meaningful way. Moving on to rack scale interconnects, the question which is top of mind for me really is whether the cost that we are investing in these rack scale interconnects is really worth the benefits that we'll get out of it. Notice that we already have large MOA models which span multiple nodes. So the status quo is really that you take multiple nodes which have not so great throughput, not so not so good latency, and deploying these large MOA models on these setups, and these are feasible right now. And the question really is that if you were to replace these not so great interconnects with this very tightly coupled interconnects, are we going to get substantial performance benefits out of that? And the place to look at here might be that in the context of inference workloads, you always have very tight latency SLOs. And in the context of these tight latency SLOs, even small sort of savings in terms of network latency or and throughput could mean that you can actually batch much larger number of requests through the system. So, so in particular, what this tight integration over larger scales might mean that you are able to push together much larger batches and therefore achieve much higher efficiency. But it's an open question as to whether that is actually going to be the case. And then at the cluster level, as I uh, talked about earlier, uh, with much larger scale-outs, optical connections become necessary. So we will probably ride the wave of all of these co-packaged optics. Whenever it becomes feasible, it will provide an alternative, lower cost and lower energy solution. And that, in some sense is going to be uh, whatever the engineering people end up providing, we just will follow along with it. But the real interesting question from a computer science perspective is whether ML can actually benefit from optical circuit switching. And what I mean by that is that with circuit switching, you can support only sparse communication patterns. And if something has a deterministic and sparse communication pattern, we can take advantage of that. ML has a lot of that deterministic and sparse communication patterns, but it also has a lot of non-deterministic all-to-all communication patterns as well. So given that, can we actually take advantage of optical circuit switching along with potentially traditional all-to-all non-circuit switched connections between every pair of GPUs? And will the communication patterns be of the nature such that this hybrid solution would actually be both cost effective and high performance? So let me just conclude by saying that this is a very exciting time for research. I particularly like the kind of research where new hardware solutions come up, and we have to both come up with new networking algorithms as well as understand what the ML system needs. And we have to do this cross-disciplinary research, which kind of combines hardware, algorithms, and ML systems. But the thing that I really want to point out is that there's actually a critical need for deeper analysis and performance models, and that we need to really understand, oh, what does it mean when you actually have higher throughput or lower latency or cache coherence? And what are the hardware systems co-design opportunities in this space? So there's lots of interesting unanswered questions on the utility and economic value of these hardware innovations, and that sounds like an exciting regime of research to be performed. So let me end here and thank you very much.